So chapter 2. So chapter 2, we're going to start talking about what matter is made up of, right? So we're going to talk about atoms. We're going to talk about how we know that atoms exist. We're going to talk about what makes up atoms, right? And then we're going to start to combine them to form molecules and compounds, okay? So the end of this, we're going to talk about how to name stuff, which tends to be kind of an Achilles heel of most chemistry students. But first, before we get to that, we need to talk about atoms. So, kind of to introduce this concept of an atom, the book that I usually use kind of gives you this thought problem, right? So if you were to take a piece of graphite from your pencil, right? So what is graphite made up of? Just say it out loud. Carbon, right? So graphite is made up of carbon, right? That's what makes up your pencil lead. So if you were to take your pencil lead, made up of graphite, and you were to cut it in half, right? And you take the half, and you cut it in half, and you take the half and cut it in half, and you did that a bunch of times, could you do that forever? Could you sit there and divide and divide and divide to infinity? Or eventually, you end up with something that you couldn't divide anymore. So the answer to the question is, eventually you would end up with something that you couldn't divide anymore. Eventually, you would end up with individual carbon atoms, okay? So a carbon atom is a carbon atom, right? If you try to cut up a carbon atom into smaller parts, you're no longer going to have carbon, okay? And so we define these little guys called atoms as these indivisible particles of matter, because again, you can't break them anymore. If you broke them, you don't actually have that piece of matter any longer, okay? Okay, so this first part of the chapter, what we're going to talk about is how we know that matter is made up of atoms, how we know that there are all these individual elements, how we can go about doing this, right? One of the big problems that I try to at least stress with respect to understanding these experiments that helped us discover that matter was made up of individual atoms was the fact that the scientists who did them, all they could measure was masses, right? Literally, all they were given is a scale and stuff, right? And they figured out that all matter is made up of these tiny little particles that you can't see and you can't actually visualize, okay? At least at the time. So now we can actually see and visualize atoms, right? So there's a technique called STM, which stands for scanning tunneling microscopy, okay? And it can visualize individual atoms, right? So again, we've led all of this history of chemistry thinking we know they're there, but we can't actually see them. At this point in time, we can actually see individual atoms, so we do know that they are there. Not only can we see them, but we can also manipulate them, right? So if you look over to the right, this is the Japanese character for atom written out in individual copper atoms, right? So an STM machine can not only look at it, but can also move little atoms around so that you can create any type of shape that you want, right? So we know they're there. Now we have STM. Now we have all of these various techniques that can visualize these individual atoms. So how did we actually get to the point of knowing about these atoms, okay? So again, as kind of a big thought idea to try to illustrate how tiny individual atoms are, I like to use this little thought thing, okay? So take a grain of sand, okay? Now imagine a grain of sand and all of the grains of sand on a beach, right? So if you look at a beach, how many grains of sand do you think there are there? A gigantic amount of grains of sand, okay? If you took one of those little grains of sand, there are more atoms in that one individual grain of sand as there are grains of sand on the entire beach, okay? So bajillion upon bajillion upon bajillion different grains of sand. There are more actual atoms in one grain than there are grains of sand on the entire beach, all right? So again, they're small, they're tiny, we can't see them, now we kind of can, but I just want to get an idea of the scope of the problem that we are dealing with, okay? Okay, so again, we talked about atoms in the first chapter. An atom is defined as the smallest identifiable unit of an element. There are 91 naturally occurring elements, so there are 91 different types of atoms. And then again, we have over 20 synthetic elements that we have synthesized in the lab. Okay, so where do we get these early ideas that matter was made up of atoms, okay? So surprisingly, you can go back to Greek philosophers to kind of get this original origin story of this idea of atoms, okay? So there were two Greek philosophers back in whenever they existed, so Greek philosophy days, named Leucippus and Democritus, okay? And they hypothesized, or they proposed, that all matter consisted of these tiny little particles, right? And that matter of one type differed from matter of the other because the particles that made it up differed in shape and differed in size and differed in the way they actually attached to one another, okay? Contemporaries of both Leucippus and Democritus were named Plato and Aristotle, okay? And Plato and Aristotle did not believe in this idea of atoms, right? They thought instead that all matter consisted of different proportions of the four elements. And they thought the four elements were earth, air, fire, and water, okay? So just looking at these four different Greek philosophers, have you heard of Leucippus and Democritus? No. Have you heard of Plato and Aristotle? So which idea do you think was propagated through history? Probably the second one, right? So Plato and Aristotle, because they had such a large influence on Western philosophy and Western thought, their idea took forth for the next 2,000 years, and these guys, Leucippus and Democritus, their idea of the atom kind of took a back seat. Okay, so flash forward 2,000 years later, what happens? So 2,000 years later would leave us about 1600s. What happened in the 1600s? The scientific revolution, right? So 1600s, we come up with this scientific revolution. And what is different about the scientific revolution comparatively to these early ideas of these Greek philosophers? What are we doing now? We're experimenting, right? We're turning science into an empirical science, right? We're making observations, we're making hypotheses, and we're experimenting about those hypotheses, okay? So we have the scientific revolution, and so instead of having these ideas and just being like, oh, I believe it, so it is, now we're actually experiments to prove these various ideas, okay? Okay, so again, we have these early ideas from Leucippus and Democritus. We're going to flash forward to the 1700s when we come up with John Dalton. So John Dalton is going to propose this atomic theory of matter, and he's going to do so coming off kind of like the basis of three separate laws. So the three laws are the law of conservation of mass, the law of definite proportions, and the law of multiple proportions, okay? So again, he takes these laws and he makes a theory out of them, okay? And the theory ends up being atomic theory. So I'm going to go through each of these individual laws and how they can kind of contribute to this idea that all matter is composed of individual atoms. Okay, so the first law was law of conservation of mass. What did that state? We've already talked about it. Can you create and destroy matter in a chemical reaction? No, right? So law of conservation of mass, in a chemical reaction, matter can neither be created nor destroyed, okay? So a nice illustration of that is this reaction here. So in this reaction, we take sodium metal, right? We combine it with chlorine gas, and what do you think we form in the process? Na plus Cl. What is that going to lead? Salt, right? So NaCl, the most common salt known, okay? So what does the law of conservation of mass say? It says that however much of this stuff, so however much of the reactants that you put in mass, in matter, it's going to equal the exact same amount of mass that comes out of the overall product of the reaction, okay? So for example, if we put in 7.7 grams of sodium, and we combine that with 11.19 grams of chlorine, how much matter, how much NaCl are we going to form? So it has to equal the same. What is 7.7 plus 11.9? Some number, right? It's written here. So this ends up being 19.6 grams of our product, okay? However much mass you put in, it's going to be the same amount of mass that you get out, okay? So how could this lead to this idea that, oh, matter is actually consistent or composed of these individual atoms? So if each atom had a particular mass to it, and you put in 10 of them, right, then you're going to have to get the exact same amount of mass out of it, right, with respect to the products. So again, this is kind of leading to this idea that all matter is consistent of individual atoms. Okay, so the second law that we deal with that helped formulate this theory is called the law of definite proportions. And we have already kind of talked about the law of definite proportions. So this has to do with compounds. Okay? So what it states is that if you have a compound, okay, regardless of where you get it from, when you break it down into its constituent elements, their masses are always going to have the exact same ratio value. Okay? So again, it's a bunch of words, doesn't really mean anything. So I try to use a nice example to illustrate what I mean by this. Okay? So let's say that we took water, right? We know that water, H2O, when we break it down, gives us hydrogen and it gives us oxygen. Okay? So this is what we mean by taking a compound and breaking it down into its constituent elements. Okay? So if we were to take, let's say, 18 grams of water, and we broke it down into its elements, so 18 grams of water, we would find that we would get 16 grams of oxygen and 2 grams of hydrogen. Okay? When we took a ratio of those two masses, so when we took the 16 grams of oxygen over the 2 grams of hydrogen, we would get a ratio of 8 to 1. Okay? That's the ratio of masses. Now let's imagine that instead of our little 18 grams of water, we went out to a different pond and got another sample of water, and instead we took 36 grams of it. Okay? We took 36 grams of our water from a different source. How many grams of oxygen do you think we would get? So when we broke it down, we would find that we got 32 grams of oxygen and 4 grams of hydrogen. What is the ratio of grams of oxygen to grams of hydrogen? 32 over 4 gives us what? 8 to 1, right? So this is what the law of definite proportion states. No matter where you get the stuff, when you break it down into its constituent elements, the ratio of the masses of the elements that make it up are always going to be the same. Okay? And again, this is kind of leading to the idea that there's a ratio of oxygen to hydrogen within water that is consistent throughout all of water. Okay, so the law of multiple proportions. So this one gets a little bit more confusing, and I'll try to make it as accessible as possible. Okay? So all of the other laws, law of conservation of mass, definite proportions, they came from other scientists. So John Dalton is coming upon these laws already. He's utilizing them to help form his atomic theory, but this is also the law that he came up with himself. So this is called the law of multiple proportions. And so what it states is when you have two separate elements, so we call them A and B, and these two separate elements can combine to form different compounds. When we compare the mass of element B that combines with 1 gram of element A, we will always find those masses or those ratios as small whole number values. Okay? So again, words don't really mean anything. The way I like to illustrate this is what I call the carbon dioxide to carbon monoxide ratio. Okay? So what this essentially says is that we go in, we find carbon dioxide, we know that this is made up of carbon and oxygen, right? So we'll call carbon our element A and oxygen our element B. Same thing with carbon monoxide. So these are two different compounds that are both composed of carbon and oxygen, right? How do I know that they're two separate compounds? Or how would they have known? When they breathed carbon dioxide, were they okay? Yeah, for the most part, right? If they breathed carbon monoxide, were they okay? No. So this is what I mean by two different compounds, right? They have two terribly different properties, okay? So if I took a sample, let's say it was a sample 3.67 grams of CO2, and I broke it down, I would find that I would make 1 gram of carbon and 2.67 grams of oxygen, okay? So I was safe, I was measuring my carbon dioxide. When I went in and I did the same thing for CO, this time, let's say I took 2.33 grams of CO. I broke it down to 1 gram of carbon, and it had 1.33 grams of oxygen. Okay, so this is what we mean by the law of multiple proportions. When we compare the ratio of masses of element B, right, for every 1 gram of element A, what do I get? When I take 2.67 and I divide by 1.33, 2, right? That's the big thing. When we compare the mass here to the mass here, and I take that ratio, this ends up being a whole number integer value. Okay, why is this a 2? How many oxygens do I have in carbon dioxide? 2. How many do I have in CO? 1. Okay, so this was a big one, right? When you compare compounds that form from 2 different elements, they make different types of compounds, and you compare their ratios, you're always going to get these 2 to 1 or 4 to 2 or some number of whole number ratio with respect to the masses. Okay? Okay, so let's go ahead and test to make sure that you guys got those 3 different laws. Okay, so I have question 2.1. Got a bunch of data. You can read it on your own. I want to know, is this consistent with the law of multiple proportions, or is this consistent with the law of definite proportions? Okay, so go ahead and get your answers in. It's a pretty little simple one. So is this consistent with the law of multiple proportions or the law of definite proportions? So multiple proportions, right? How do I know that? Without even reading any of the stuff, what am I comparing? 2 different compounds, right? What are those 2 different compounds composed of? Nitrogen and oxygen, okay? And if I wanted to show that this was consistent with the law of multiple proportions, what mass would I be comparing? I'd be comparing the mass of oxygen, right? Because this is oxygen for every 1 gram of nitrogen, oxygen for every 1 gram of nitrogen. And what would be that small whole number integer value when I compared the masses? Did anyone compare it? 0.5704? Okay, right? So again, when we compare these masses, this is mass of oxygen for every 1 gram of the other element, you should get some sort of small whole number value, okay? Okay, now it's simple, super easy. Let's try another one, same question. Is this consistent with the law of multiple proportions or the law of definite proportions? I only illustrate these guys because you'll probably see something very similar to this on an exam, so. Okay, so most of you guys have gotten this correct. Is this definite or multiple? Definite proportions, right? And so if I were going to utilize this to illustrate that this is the law of definite proportions, which masses would I be comparing? So I've got carbon dioxide. It's one type of compound. In one sample, I get 9.6 grams of carbon for every 25.6 grams of oxygen. What is the ratio of those two? So if I take the big one, 25.6, I divide it by the small one, it gives me a ratio of 2.67. Am I going to get the same exact thing when I compare 21 to 8? Yes, right. That is because it is a law. It is the law of definite proportions, okay? Okay, so those are the laws. So John Dalton, he looks at these laws, he says, oh, I have a theory to explain these laws, right? And he proposes his atomic theory, okay? It has 4 separate little postulates. Some of these are still correct to this day. Some of them are not. Maybe you guys can figure out which ones are not exactly correct, okay? So the first postulate states that each element is composed of individual indestructible particles called atoms, okay? So that's the big one, and that's still correct to this day. Number 2, it states that all atoms of a given element are identical to one another, and they are different from atoms of a different element, okay? So for example, oxygen, that's an element, right? The atoms that make up oxygen are identical to one another. They are different than the atoms that make up another element, right? Something like nitrogen, okay? Is this still true? Kind of? Somewhat. So we'll talk about how this kind of deviates from Dalton's theory in a few different slides, okay? Number 3, in a chemical reaction, you cannot convert one element to another, right? So in a chemical reaction, you can't take oxygen and turn it into nitrogen, right? Is that true? In a chemical reaction, no. But can we convert elements into other elements? Yes, in some sort of radioactive process we can. So this ends up not being quite so true. And then number 4, when we make compounds, all we're doing is we're combining atoms of different elements together and forming bonds, okay? So this, coming back to the compound idea, in multiple proportions and definite proportions, when we make something, it's just atoms of different elements combining together to make this new thing. We're not actually making like the 121st element or anything like that. Okay, so we have this idea that matter is consistent of individual atoms, okay? We have this atomic theory, we're going to move forward with that. So now the question is, if you know these little atoms that are drawn on my little PowerPoint here, what do we depict them as? Just spheres, right? So is that what they are? Are they just little individual spheres? No. So the big question is now, what are atoms actually made of? Are there individual tinier particles that make up these atoms, or are they just little spheres that float around in empty space? So the answer to that is that atoms are made up of smaller individual particles. We call these subatomic particles, right? Because they're below the atomic scale, okay? We're going to talk about the discoveries that led to our subatomic particles, or the discovery of our subatomic particles, through 4 different experiments, okay? First one we're going to talk is cathode ray tubes. The second one, I'm going to discuss the Millikan's oil drop experiment. Third, I'm going to discuss Rutherford's gold foil experiment, and that kind of ties in radioactivity. I need to take this out because I took out the slide. Okay, so before I start on this, I want to briefly talk about electrostatic interactions, okay? Just to kind of remind you about how charged particles behave with respect to one another, all right? So let's say I had something that was positively charged. Now you can't see the positive. So I had something that was positively charged, and it was around something that was negatively charged, okay? Would they be attracted to one another, or would they be repulsed by one another? They would be attracted, okay? So when we have opposite charges, there is a mutual attraction between the two. You probably can't see this. So this is opposite charges. Now what happens if I have similar charges, right? What happens if I have a positive charge molecule and it's being brought close to another positive charge molecule? What are they going to do? they're going to be repulsed by one another, right? So they're going to push each other apart. Same thing if I have a negative charge and a negative charge, they're repulsed by one another, okay? So this, when we have same charges, this is repulsion. They don't like each other. They don't want to be around one another. Okay, so then last little bit, if I have a positive charge overall and I combine it with a negative charge, what is the overall charge of the thing? Neutral, right? So a positive and a negative, they'll cancel each other and they'll make something charge neutral, okay? Okay, so now with that in mind, let's go ahead and get into the discovery of our subatomic particles. Yes? They are matter. Yes, they are matter. So if we get down to the subatomic particle scale, the atom of the element is defined by the number of, let's say, protons in the nucleus, right? If I try to take one of those protons away, I no longer have that element, right? Because the atom, the element itself, is defined by the number of positive charges that are located in the nucleus. So if I broke up those subatomic particles, I would no longer have that element anymore. Does that make sense? Yeah. Kind of. Okay, so the first subatomic particle that was discovered was the electron, right? So I say the electron, what charge do you think about, right? Most people are familiar with what an electron is, right? It is a negatively charged particle. Negatively charged particle. But where do the electrons come from? How do we ever figure out that there are electrons to begin with, okay? So the discovery of the electron came from studies that were concerned with things called cathode rays, okay? So cathode rays had been known about for a while. They had been investigated, they've been studied by a lot of different people. And what they essentially are is they are rays that are derived from something called a cathode ray tube, okay? So what a cathode ray tube is a glass tube that is evacuated inside. Evacuated. Meaning there is no air inside the tube, okay? On two ends of the tube, there are electrodes, okay? So electrodes are usually made up of some specific metal. So a metal and a metal. And what happens in a cathode ray tube is, in this evacuated glass tube, two metal electrodes on either side, an electric charge or voltage is essentially discharged between the two electrodes, okay? What happens is a beam of light or a beam of particles essentially originates at the negatively charged electrode, what we call the cathode, and goes towards the positively charged electrode, which is what we call the anode, okay? So it's not necessarily a beam of light. We only see this because there's a fluorescent screen, but it's a beam of particles, okay? So if we have something that's deriving at the negative side of the electrode and going towards the positive side, why do we think it's a negatively charged molecule? If it's negatively charged, what side is it going to be attracted to? The positive, right? And so this is how they knew it is going towards the positive side. It has to be itself a negatively charged particle because it's attracted to the anode, okay? So they knew it was negatively charged. Also, one big important point to note is that you could make these cathode rays no matter what type of metal electrode you were using, right? So if this metal electrode was silver, if it was gold, if it was platinum, no matter the metal that you actually utilized, you would still get the same exact type of cathode rays, okay? So this kind of illustrated that whatever thing was coming out of this was fundamental to all matter, because it didn't matter the material you put there, you're getting the exact same thing, okay? So negatively charged, didn't matter what type of material you were using for the electrode, and they traveled in straight lines. That was kind of important. Okay, so the first person to kind of postulate that this beam or this cathode ray consisted of a beam of these tiny little particles, which they called electrons, was this guy named J.J. Thomson, okay? And so he proposed that these cathode rays, again, were these beams of these negatively charged particles, and what he was able to do was he was able to essentially measure what is called the charge to mass ratio of the electron, okay? So how did he do this? So number one, these cathode rays could be deflected by both electric fields as well as magnetic fields, okay? So if you put an electric field around a cathode ray, which side of the electrode do you think it would go to? So it would go to the positive side. They could also be deflected by a magnetic field. So you could apply a magnetic field and they would also deviate from their linearity. By essentially sitting here and modulating the electric field to magnetic field ratio, he was able to calculate the charge to mass ratio of this cathode ray. Okay, and it ends up being this minus 1.76 times 10 to the 8th coulombs per gram. Okay, so it's important to note, you don't really need to know how he got that, but this is what he gets out of it, charge to mass. Okay, does that mean that we know the actual individual charge of an electron? These particles that are making up these cathode rays? No, right? Do we know the individual mass of an electron? No, right? All we know is how many charges we get per gram of these things, okay? All right, so the next experiment, which is where we get both the mass of a single electron as well as the charge of a single electron, is via this one called Millikan's oil drop experiment, okay? So this one I think is kind of neat because it'd be interesting to actually try to do this in real life. So the way this one was set up is this guy, Robert Millikan, he had this little apparatus, okay? And in this apparatus, it had two separate chambers. So it had a top chamber, and then it had a bottom chamber, okay? And so what he did in this top chamber is he had this tiny little, like, mister or vaporizer that had oil in it, okay? And every time he squeezed this little vaporizer, a fine mist of oil droplets would go into that top chamber. Okay, so you squeeze out this little fine mist of oil droplets. What's their tendency going to be because of the force of gravity? What are they going to do? They're going to fall, right? So he squeezes out his fine little oil droplets, and they begin to fall towards the bottom of this top chamber due to the force of gravity, okay? At the bottom of this top chamber, there is a tiny little pinprick hole, okay? And so the majority of these little oil droplets are just going to hit, and they're not going to go anywhere. But every once in a while, you're going to get one of them that goes through this tiny little pinprick hole, okay? And when they do, they enter the second chamber. And this is where the real magic happens, in the second chamber, okay? So once these individual oil droplets start going to the second chamber, they are bombarded with a source of ionizing radiation. So he essentially just bombards them with X-rays. What this is going to do is it's going to impart this negative charge. Whatever this negative particle is, it's going to impart it to these individual oil droplets, okay? It's not just going to essentially impart one. It's going to impart multiple, like 100 or 200 or whatever. There's going to be multiple of these charges on these tiny little oil droplets, okay? So again, they're falling because of the force of gravity. But what he has here is he has, again, two electrodes, okay? We're imparting negative charges to these guys. When he applies an electric field, they're naturally falling because of the force of gravity, but when he applies an electric field, they're going towards a negative charge electrode, okay? What's going to happen eventually as he starts to ramp up that electric field that the two electrodes are applying? They're falling naturally, they're negatively charged, they're going towards the cathode, which is also negatively charged. What's going to happen? Eventually, that electric field is going to be strong enough that it's going to repulse that little oil droplet with its negative charges, right? So much so that it essentially can just suspend it in midair, okay? So he does that. He measures the voltage that is required to halt the progression of these little oil droplets, and then what he does is he looks at them through this little microscope, okay? So this is where it gets, I just don't know how they go about doing some of this stuff. He looks at them through this tiny little microscope, and what he measures is the radius of each little individual oil droplet, okay? With that, he knows the density. He measures the radius so he can get the volume. So he's going to solve for the mass of these individual oil droplets, okay? With the mass of the oil drop, as well as the charge or the voltage that was required to halt their progression, he is able to figure out that each oil droplet has some whole multiple charge of this minus 1.6 times 10 to the minus 19th coulomb, okay? So it's not that one of the oil droplets had this charge, it's that each individual oil droplet had some whole number multiple of this specific charge, okay? So this ends up being the fundamental charge of a single electron, and that's how he figures it out. So once he has the fundamental charge of a single electron, and he combined that with J.J. Thomson's measurement, which was the charge to mass ratio, he was able to determine the mass of an individual electron. Okay, so this guy, 9 times 10 to the minus 28 grams, this ends up being 9.1 times 10 to the minus 31st kilograms, at the time was surprising, okay, because this is very, very, very small. The smallest atom at the time was hydrogen, which is still the smallest atom that we have. The mass of one individual electron was 2,000 times smaller than the mass of hydrogen, okay? So overall, what's going to happen with respect to the electron is that the electron, as a subatomic particle, gives the atom a negative charge, but it contributes no mass at all because the mass of individual electrons are so small, okay? So electrons, we get our negative charge, but they contribute no mass. Should I go on? That's the question. No, I'm going to stop here because I get really animated with Ernest Rutherford. So I will stop for the day. So again, on Thursday, there is no... I forgot to start recording. Okay. Yes. So the slight angle was essentially just the alpha particle grazing the nucleus, getting a little bit of a repulsion that leads it off to the slight deflection. The actual like hitting the nucleus head on, that's what was essentially shooting those alpha particles straight back. And it's again just the force of the repulsion of the positive charged particle with the positive charged nucleus. When they hit, it was so dense that force just shot it straight back. Does that make sense? Yeah. Okay. Okay, all right, so Rutherford's gold foil experiment. We already had the electron. We knew it had no mass. Now we have the proton, okay? The proton is the big thing that comes out of this experiment. So protons are what are in the nucleus, right? This tiny little space of the atom. Protons have mass, right? So they give us mass, and they also give us the positive charge of our atom. This is what's making our atoms electrically neutral. So this is our positive charge particle. Another part of the nuclear model is the fact that these protons are contained in this nucleus, and this nucleus is very small with comparison to the remainder of the atom. The majority of all atoms are just empty space, okay? And the empty space is where these electrons are, these negatively charged particles that don't have any mass associated with them, okay? So the majority of the atom, empty space with electrons, we don't know what they're doing yet. The nucleus, we have our positive charge, and we also have all of the mass of the atom, okay? So just to note, with respect to protons, I frequently will use this to denote a proton, and with respect to electrons, I will usually use this to denote an electron, okay? Okay, so is that it? We've got our subatomic particles. Everything's great. We've got our proton, we've got our electron, we get charge neutrality, everything's happy. Is that it? No, right? So there's one more. It took a little longer to discover, and that is the neutron, okay? So although Rutherford's gold foil experiment and his nuclear model of the atom was successful, it didn't quite explain everything, okay? So for example, hydrogen has one proton, right? It has one proton in its nucleus. Helium, on the other hand, has two protons in its nucleus, right? And if protons are the only thing that's adding mass to an atom, then helium should be twice as heavy as hydrogen. But in reality, helium is 4 times as heavy as hydrogen, okay? So protons by themselves can't explain that. So instead, we have another subatomic particle called the neutron. And this was proposed and essentially discovered by this guy, James Chadwick. Neutrons are neutral, right? So they don't add any type of charge to the atom. And so I will frequently denote them, this little n with a 0 superscript. But they do give us mass. So we have no charge here, but they do add mass to the atom, okay? To explain helium, helium has 2 protons, but how many neutrons does it have as well? it also has 2 neutrons in the nucleus, right? So this is why helium is 4 times as massive as hydrogen. Hydrogen has 1 proton. How many neutrons does it have in the nucleus? 0, right? So hydrogen only has a proton. Helium has 4 things that are giving it mass. That's why it is 4 times as heavy as hydrogen, okay? Okay, so those are our subatomic particles. That's it. That's all 3 that we're going to study for the most part, okay? So we have our protons. Our protons, again, are positively charged. They do give mass to the atom. We have our neutron. This guy is negative, or not negative, pardon me, neutral charge. They give mass as well. And then we have the electron, which is our negatively charged particle, which does not contribute any mass to the atom, okay? A couple of things to note. When we denote these charges, do you guys remember what the real actual charge of an electron was, a single electron? It was like 1.6, it was a negative, times 10 to the minus 19th coulomb, right? That would be a hassle if we were trying to write, oh, we have an electron charge, or we have this charge. So we essentially use what are called relative charges, okay? So just note that when we're using a +1 or a -1, it's going back to this, but we don't want to have to write this every time. So when we say -1, we mean the charge of 1 electron. That's what we mean by relative charges. We do the exact same thing for mass, right? So with respect to the mass of the proton, a proton ends up being like, I don't know, 1 times 10 to the minus 27th kilogram. Very, very, very small. So instead of having to write this over and over and over again, we utilize a unit called atomic mass unit, okay? So it's kind of been normalized so that 1 proton equals approximately 1 atomic mass unit. We don't have to write these masses over and over again. So we abbreviate this AMU. This is what we mean by atomic mass unit. And it is technically defined as 1/12 the mass of carbon that has 6 protons and 6 neutrons in its nucleus, okay? Same type of thing though, so we can use these numbers freely. We don't have to actually go back to these tiny, tiny numbers. We use AMUs to denote mass, and we use relative charge to denote positive and negative charges. Okay, so elements. So now that we have our subatomic particle, why do we have all these various elements? How do they differ from one another? So the most defining characteristic with respect to an element is the number of protons in its nucleus, okay? An element is defined by how many protons are in its nucleus. So for example, carbon has 6 protons in its nucleus, right? If you're dealing with something that has 6 protons in its nucleus, you're dealing with carbon. There's no other thing, right? What if I said, oh, I have carbon, but it has 7 protons in its nucleus? Is that possible? No, because that's a different element, right? Who has 7 protons? Carbon, nitrogen. Nitrogen has 7 protons in its nucleus, okay? We denote the number of protons by something called the atomic number, okay? And we give it this chemical, or this symbol Z. So Z refers to the number of protons in the nucleus. And it is defining for the element. How else do we depict elements? What else is a unique identifier for each individual element? Chemical symbol, right? So another way that we can uniquely identify an element is via its chemical symbol. And we talked about that last chapter. What is the chemical symbol for, say, oxygen? O, right? So each element has its own chemical symbol. Each element is also defined by the number of protons in the nucleus. Okay, so here's a beautiful periodic table. So if you note, as we go from left to right, the atomic number is up here. It's right above the chemical symbol. And again, what does this refer to? What is this telling us about the element? How many protons are in the nucleus, okay? So it's usually always listed either above the element or off to the side in a corner, but you're looking for a whole number, and that is the atomic number of the element. Okay, so a couple more things. Now, I just said that each element depends on the number of protons in the nucleus. Does that mean that each atom of an element has the same number of neutrons in the nucleus? No, right? So while if we're talking about carbon, it has to have 6 protons, it doesn't necessarily have to have 6 neutrons, right? So different atoms of an element can differ in how many neutrons are in the nucleus, okay? These differences, right, so these different atoms of an element that have different numbers of neutrons in the nucleuses, these guys are called isotopes of that element. So for example, if we had neon, so neon has 10 protons. So if you're dealing with something that has 10 protons, you're dealing with neon. Neon, though, can have 10 neutrons. It can have 11 neutrons. It can also have 12 neutrons, okay? So each of these guys is a different isotope of neon, okay? All of these guys are different isotopes. So the fraction of each isotope that you get in a sample is actually essentially a constant. It's called the natural abundance of the isotopes of a given element, okay? So for example, the natural abundance of neon with 10 protons and 10 neutrons is 90.48%, okay? So 90% of the time when you go out and get a sample of neon, you're going to find this isotope with 10 protons and 10 neutrons in the nucleus, okay? 9% of the time, you're going to find the isotope that has 10 protons and 12 neutrons in the nucleus, okay? So again, these percentages or these fractions are constant, and they're called the natural abundance of each individual isotope. Okay, so if we have two isotopes, and they do vary in their number of neutrons, what's that going to affect? Right, because neutrons give mass to the atom as well as protons. So if you have things with different amounts of neutrons in them, then it's going to affect the overall mass of each individual atom, okay? So because of that, we have to define the atomic mass for each individual isotope. So we give this atomic mass, we call this the mass number, okay? And the mass number is given this symbol A, and it's defined as the number of protons and the number of neutrons in the nucleus, okay? So when we write these isotopes, we usually use this notation where we write the chemical symbol, then we'll write the mass number in a superscript and the atomic number in a subscript to the left, okay? So let's say, again, we go back, we're dealing with something like carbon. And I write in my little top corner, 13, and in the bottom corner, nope, that's not right, I write 6. How can I determine how many neutrons this isotope of carbon has? So I've just defined A as the mass number, right? What is the mass number? What is it a sum of? Protons plus neutrons in the nucleus of this isotope. How can I figure out how many neutrons are in this? If I know that A, the mass number, is 13, do I know the number of protons for carbon? Yes, it's identifiable by the atomic number, which is written, but it's also identifiable by the chemical symbol, right? It's carbon. It has to have 6 protons in it. So 6 plus the number of neutrons, how many neutrons does this isotope of carbon have? 7. Okay, so you can always use the mass number to determine how many neutrons you're actually dealing with in an isotope. Okay, so one more thing and then we'll do a question. This kind of notation I like. I think it's pretty. It looks nice. But is this and this, is it kind of repetitive? Right? So when I say neon, you know it's 10, right? You know its atomic number is 10. So another way that you can denote these isotopes is using this notation, where you give the chemical symbol and you just follow it with the mass number, okay? So again, with respect to the mass number, this guy is number of protons and number of electrons. This is going to give you the exact same amount of information as the previous one gave you. And then one more thing with respect to this. We talked about protons and neutrons with respect to these isotopes. What can we assume about the electrons right now? So again, if we're dealing with carbon, we'll say it's carbon 12 this time. Don't know why I keep doing that. How many electrons does this have? How do I know that? It's neutral, right? It's charge neutral. There's no charge with respect to this, So we have to have as many electrons as protons. Have to be the exact same if we have a neutral molecule, okay? So if I gave you this, would you be able to figure out the number of electrons, the number of protons, the number of neutrons? Yes, okay? All right, so let's go ahead and try that. So I'll put this on Socrative. I think I only asked you about one of these, but go ahead and try the 3, and then we'll go over them. Okay, so let's go ahead and go over these. So I only asked again one on Socrative, but there were 3 parts. So hopefully you went through the B and C. But for A, what are we dealing with? We're dealing with chlorine. So what was the atomic number of chlorine? What is it again? Sorry. 17. No, I did that. 17. What is the mass number if we have 18 neutrons? If it's the isotope with 18 neutrons? 35. And then that's it. Chemical symbol was the chemical symbol for chlorine? Cl. So again, using that notation from before, we would write this isotope as Cl, 35 up top and 17 down below. Okay, so B, we have chromium, right? How many protons, electrons, and neutrons are in this isotope of chromium? So how many protons are there? 24. Again, that comes from the atomic number. How many electrons are there? 24 as well. It's a neutral molecule. And then how many neutrons are there? 28? Cool, I didn't have to do any math. All right, so 24, 24, 28. Again, we get neutrons by subtracting the atomic number from the mass number. And then the last one, we've kind of already done, dealing with carbon with 7 neutrons. What's the atomic number of carbon? 6. And then if it has 7 neutrons, what is the mass number? 13. Easy, easy stuff. Okay, so last little bit of vocab with respect to individual atoms. So again, isotopes differed in the number of neutrons in the nucleus, okay? We have another I word, which is also going to differ between different atoms, and this is called ions, okay? So, sometimes in a chemical reaction, molecules or atoms can lose electrons and gain electrons, okay? And when they do so, they're going to form what is called ions. So for example, if I have lithium, right, if we looked at the periodic table, lithium has 3 protons. If it's neutral, how many electrons does it have? 3 as well, right? And let's say in a chemical reaction, lithium goes through and loses an electron. How many protons is he going to be left with? Still 3, because it's lithium, right? It's defined by the number of protons. How many electrons if they lose 1? We've lost 1 electron, we are left with 2 electrons, okay? If a proton is a positive charge and an electron is a negative charge, if we have only 2 electrons versus 3 protons, what is my overall charge of the molecule? Positive 1, okay? So, lithium can lose electrons, right? It can lose electrons and form positive charged ions. Positive charged ions are called cations, okay? Again, ions just differ in the number of electrons in the outer orbitals of the atom. So when we lose an electron, we form a positive charged molecule. This is called a cation. On the other hand, if we had fluorine, fluorine naturally has 9 electrons and 9 protons. If fluorine gains an electron, how many electrons is it going to have? 10, right? It still only has 9 protons. So what would be the overall charge if something like fluorine gained 1 electron? A -1, okay? So this is another type of ion. This is a negatively charged ion, and these are called anions, okay? So cations are positively charged, anions are negatively charged, and this comes from either losing an electron or gaining an electron, okay? Okay, so that's kind of isotopes, subatomic particles. We have now the definition for elements with respect to protons. So now we're going to move out and talk more in general about various periods or various areas of the periodic table. Periodic table of elements, okay? So how did the periodic table come about? Why is it arranged the way it is? It's a very good question, right? So the origin of our current model of the periodic table, the way that we look at it today, comes from this guy, Dmitry Mendeleev, who was a Russian chemist back in the 1800s. Okay, and what he did was he took all of the elements that were known at the time, so let's say hydrogen through calcium, and he ordered them. So he just put them out and ordered them in order of increasing mass, right? So hydrogen at that time and still today is the lightest atom, whereas calcium was the heaviest, okay? And what he noted was that every once in a while, you would start to see various properties reoccur. Okay, so for example, lithium is very reactive. It's a very reactive, shiny metal. Sodium is very similar to how lithium reacts. It's a very reactive, shiny metal. If you put both of these in water, they will violently explode. Okay? Potassium is also very reactive. It's a very reactive, shiny metal. It will also explode in water. How many elements separate lithium from sodium and sodium from potassium? 8, right? So we noted that every 8 elements, you started to get very similar properties coming back over and over and over, okay? Same thing for beryllium. Beryllium behaves just like magnesium, just like calcium, okay? So what he did was he took this ordering and he put in the same column things that essentially had very similar chemical properties. And he got this, right? Kind of looks like the periodic table, right? What's different between this and our current periodic table? We have a lot more, number one, right? What else? The problem with Mendeleev and what he did here was he ordered it in order of increasing mass. In reality, these guys need to be ordered in order of increasing atomic number or increasing protons in the nucleus, okay? So our current periodic table, lots and lots and lots of stuff, but also they are ordered in order of increasing atomic number and not overall increasing mass, okay? All right, so when he formulates this, it's really pretty, nice and beautiful. He also comes up with this periodic law, okay? And this periodic law essentially states that when you order these guys in order of increasing mass, you start to get these sets of reoccurring properties periodically. Great, that's where we get the periodic table from, so the periodic word. Okay, so this is the current manifestation of the periodic table. There are lots and lots and lots of elements. There are up to 118 all the way down here, okay? There are a lot of different ways in which we can categorize various areas of the periodic table. So the first way I'm going to talk about is by differing types of elements, okay? So the first way we're going to categorize the current periodic table is by dividing metals from nonmetals and from what are called metalloids. Okay, so we'll start with metals. Where are metals? How do we know where a metal is on the periodic table? So there's a very helpful little dividing line, little zigzag right here, okay? Everything to the left of this is a metal, okay? So everything to the left of this nice pretty little zigzag is a metal. Everything to the right is a non-metal. And these little elements in purple here, these guys that kind of go along the zigzag, these are what we call metalloids, or we also call them semi-metals. Okay, so metals, everything to the left of that zigzag, non-metals, everything to the right. With respect to metalloids, we kind of ignore them anyways. So just always assume if it's to the left, it's a metal. If it's to the right, it's a non-metal. Okay, so what are kind of some of the properties of metals? Can anyone name a property of a metal? When you think of a metal? So number one, they're hard. What is their normal physical state at room temperature? Solids, right? So most of the time, they are solids at room temperature. Because of that, they're very good conductors of electricity as well as heat, right? So they can conduct heat and electricity well. What type of metal makes up the just general things with respect to all of our power adapters and everything? Copper, right? So copper is frequently used in the generation or the transmission of electricity, okay? A couple other things. Metals like to lose electrons when they undergo chemical reactions, okay? So if it lost an electron, what type of ion would it form? So losing electrons would give us positively charged ions. What are these called? Cations. Okay, so metals like to lose electrons in chemical reactions. They will form positively charged ions. We call those cations. Okay, so metals, solid, good conductors of heat and electricity, and they like to lose electrons. What about the nonmetals? So the nonmetals, again, are these guys. In green, there are much fewer of them comparatively to the metals. So with respect to the nonmetals, their physical states actually depend on which nonmetal you're looking at, okay? So 5 of the nonmetals are solids at room temperature. So this is things like carbon and phosphorus. 1 is a liquid. This is bromine. And then 11 of them are gases. So the majority of nonmetals are actually gases at room temperature. So considering their gases at room temperature, do you think they're going to be very good conductors of heat or electricity? No, right? So they are poor conductors of heat and electricity. And most important, moving forward, nonmetals like to gain electrons in chemical reactions, right? So if they gain electrons, what is the charge of their ions? They tend to form negatively charged ions if they're gaining electrons, if they're taking electrons from things. What do we call these negatively charged ions? This is anions. So nonmetals like to form anions or negatively charged ions in chemical reactions. That is in comparison to metals, okay? And then what is the third one? We have metals, nonmetals, and we have that zigzag, and it's like those elements. Metalloids, okay? So nobody really likes metalloids except people in the semiconductor industry, okay? So these metalloids, they kind of exhibit mixed properties, but the most important property that they do exhibit is the fact that their conductivity, their electrical conductivity, is very highly temperature dependent, okay? So this is what we utilize in producing semiconductors, and again, this is because at high temperatures, they're very conductive, whereas at low temperatures, they're not very conductive with respect to electrical conductivity. Okay, so that's one way that we can categorize all of the elements on the periodic table. One other way that you guys have to be familiar with is this way, right? Dividing the elements via what are called main group elements and what are called transition elements, okay? So there are 8 different columns that contain all of the main group elements. So we have the first 2 columns and then the last 6 columns, pardon me. In the middle here, we get our transition elements, right? There are 10 columns that go across with the transition elements. How do you think these guys differ with respect to one another? So main group, the reason why we like them and why they tend to be what we study more often than not is because they are very predictable based on their position in the periodic table. We can predict what lithium is going to do in a chemical reaction. We can predict what fluorine is going to do, how many electrons it's going to lose or gain, etc., right? Everything in the middle here, all these guys, are not predictable. And we can't predict what size they're going to be, what type of electrons they're going to lose based on their position in the periodic table. Okay, so main group are predictable. Transition group, transition elements are not predictable based on position. Okay, so there's one more little categorization that I want you guys to be aware of, and that's the difference between groups versus columns, okay? Groups versus periods, okay? So groups are defined as columns. So when I talk about groups, I'm looking at elements that are all in the same exact column. Periods, on the other hand, are referring to rows in the periodic table. So when I say period 1, I'm referring to all of the elements in that first row of the periodic table, period 2, etc. Okay? With respect to groups, there are a couple of different ways that we distinguish it. Okay? So notice that there are 18 columns going across, right? There are 2 ways that we denote this. The first way is kind of the old way, where we define all of the main group elements with this letter A afterwards. So for the main group columns, we would call it 1A, 2A. We entirely skipped the transition metals, go to 3A, so on into 8A. And then we would give the transition metals the B. So B would be, or B refers to transition elements. And again, we're going from 3 all the way to whatever, okay? This is helpful long-term in knowing this kind of denotation where you have 1 to 8 with respect to main group, but you can ignore these guys with respect to the transition elements. The other way is just going 1 through 18. Okay, so main group would be columns 1 and 2, and then 13, 14, 15, so on. Transition elements would be 3 through 12. So groups, the reason why we introduced this at this point in time is because all of the elements in the same column or in the same group right, have very similar chemical properties. Okay, so this is what Mendeleev found. He found that when he ordered things, he started to see these exact same properties recur over and over and over. That's why we have these guys in the same column, because they all have very similar chemical reactivities. So now we're going to briefly go over a couple of these very similar chemical groups with respect to ones that are kind of well known. I just said this. Okay, so first one we're going to talk about is noble gases, right? Where are the noble gases with reference to the periodic table? They're all the way to the right? Are these guys metals or non-metals? Non-metals. Why do we call them noble? They have a full valence shell. They don't do anything, right? They're completely inert in chemical reactions. That's why we refer to them as noble. They just sit there and they don't do anything. What is probably one of the most common noble gases that you will find in the world, that you utilize maybe at birthday parties, etc.? Helium, right? So we use helium, which is a noble gas, to fill up balloons. Why would we do that? Let's imagine we filled up the balloon with hydrogen instead. What if someone came around with like a cigarette or something and hydrogen was in this balloon? Big explosion, right? So helium, because it's so noble, won't react, right? And that's why we will fill children's balloons with it and know that nothing will happen because of that, because it is a noble gas. What about another common noble gas? Neon. Where do we find neon at? Neon lights, right? We'll talk about neon lights and neon signs when we talk about the atomic structure of atoms. Okay, so another common group number 1. This is first column of the periodic table. These are the alkali metals, right? So these are things like lithium, sodium, potassium, and so on. They're metals, right? First column of the periodic table. So what type of ions do they like to form? Cations, right? Metals love to lose electrons, so they will form cations. These guys are super reactive, right? So nice little thing, you take a marble-sized piece of sodium, you put it in water, and you get a violent explosion. It's the exact same thing for lithium, exact same thing for potassium. So as is, without actually being the ion form, these guys in their metal, in their solid form, are extremely reactive. So group 1, then we'll move to group 2, next column in the periodic table. What are these guys called? Alkaline earth metals, right? These are things like beryllium, magnesium, calcium. They're reactive, right? But they're not as reactive as the group 1 metals. They still will be fairly reactive, but they won't be as violent of an explosion when you put them in things like water. Again, being a metal, what type of ion would this like to form? Again, cations. These guys are all metals. So now we're going to skip and go back over to the nonmetals and talk about the halogens. Okay, so the halogens are a bunch of nonmetals. Most of them, well, some of them are gases, right? So things like fluorine, chlorine, these guys are gases at room temperature. What was bromine again? What is its physical state? This guy was a liquid. Oh, right here was a liquid. Iodine is kind of a liquid solid. And I actually don't know what astatine is. I actually don't know what the form it takes at room temperature. And it doesn't tell me on my slide, so I can't tell you either. I'm sorry about that. Okay, so halogens, nonmetals. What type of ions do they like to form? These guys love to take electrons from people, form negatively charged ions. These like to form anions, okay? Would it be safe to put any of these in chemical or any type of balloon for your party? No. So chlorine is toxic. If you breathe it, you die. Fluorine, probably the same thing. Pretty much all of them you shouldn't be around for the most part. Okay, so I've been alluding to this whole ion thing, and we've been talking about these main group elements. So remember, the main group elements are very predictable, right? You can look where they're at and know exactly what type of ion you're going to form, okay? So how do we predict that? So a good rule of thumb is that metals and nonmetals are both going to want to have as many electrons as their nearest noble gas, right? Everyone wants to obtain a noble gas configuration, okay? So for something like lithium, right, lithium as a neutral molecule has 3 protons and 3 electrons. Who is lithium's nearest noble gas? You can go forward, but you can also go in reverse, right? So here's who is the closest person with respect to lithium? Helium. How many electrons does helium have? 2, right? So helium has 2 electrons. For lithium to obtain the exact same amount, what does it need to do? It needs to lose 1 electron. What type of ion or what charge of ion would it form? A cation, and most importantly, it would be a +1 charge, right? We can predict that based on where lithium is at. What about something like magnesium? Magnesium is in group 2. Who is its nearest noble gas? Maybe smart to consult the periodic table. So we'll even ahead, right? Magnesium, if we go in reverse, nearest noble gas is chlorine? Its nearest noble gas is, oh, that's a halogen. Neon? Yes, neon. Okay, neon, which would be 1, 2, 3, neon, helium. Okay, all right, so magnesium, as is, periodic table, has 12 electrons, 12 protons. Helium has 10 electrons. How many electrons does magnesium need to lose to get to neon? 2. So if it loses 2 electrons, what is the charge going to be? +2. So magnesium, 2+. So just as a little note with respect to writing these things, with lithium, it lost 1 electron. We didn't put the 1, right? We just put the plus. Anytime you're starting to move into multiples of charge, you do need to denote that. And the way we denote it is kind of weird. We don't write +2, we write 2+, okay? Just a note on notation. Okay, so for all of these guys, you can predict what charge ions they're going to form based on their position in the periodic table, because again, they're all main group elements, okay? So for the halogens and all of these guys, their closest way to get to the nearest noble gas is to gain stuff. Whereas for the metals, it's to lose electrons instead, okay? So all of the halogens need to gain 1 electron. Oxygen, sulfur, selenium, these guys need to gain 2 electrons. So there'll be 2- anions. Nitrogen needs to gain 3, so on and so forth. You should be able to predict the charge of the ion based on its position solely in the periodic table. Okay, so let's go ahead and try that. A couple questions. So I want to know what the predictable charge is for these various elements. But the nitrogen isn't on the socrative quiz. Sorry, I tried to change it before class. And then rubidium has the wrong charge as well. The answer. Every day. Every day. Okay, so go ahead and get your answers in. Again, there's some errors in this, but we'll go through all of them anyways. So for aluminum, what type of charge would it form? And I want to know the specific actual charge, not just that it's positive. So 3 plus, right? 3 plus, or you could have put positive 3 and been correct. Why is this again? So aluminum naturally has 13 protons, 13 electrons. Who is the nearest noble gas for aluminum? So again, you can go forward, but you can also go in reverse, right? If we go back to neon, neon is the nearest noble gas. It has 10 and 10. If we went forward instead to argon, argon has 18 and 18. So who's closer for aluminum, neon or argon? Neon, right? And so to get to neon, how many electrons need to be lost? 3 electrons. If we lose 3 electrons, we have 3 more protons than electrons, so it's a 3 plus molecule, okay? This guy loses, we have 13 protons plus 10 electrons. 3 more of these guys give us a 3 plus. What about sulfur? Here, sulfur is a nonmetal, so what type of charge will it form? Negative, regardless, it's going to gain electrons. How many should it gain? 2, right? So sulfur is going to form a 2 minus. It's going to obtain the same electron configuration as argon, okay? Nitrogen, didn't put in here, but what would you predict with respect to nitrogen? So number 1, negative, right? So negative because it's a nonmetal. How many electrons does it need to gain? 3. It needs to gain 3 electrons. It is at 7. It needs to gain 3 to get to 10, which is neon. Nitrogen, neon. So this would be a 3 minus. And then the last one is rubidium, which was inserted incorrectly. Rubidium is an alkali metal, right? It's metal. What type of charge should it form? Positive. It's an alkali metal, so it's in group 1. So what is the positive charge going to be? What is the magnitude? Should just be a plus 1. So rubidium should just lose 1 electron to make a plus 1 ion. So this you should be super comfortable with moving forward, which it seems like most of you guys are. It's good. So one more thing before we leave today. We're going to talk about something that we haven't yet talked about with respect to the elements little box in the periodic table, right? So we have talked about atomic mass. No, we haven't. We have talked about atomic number, right? We've talked about the chemical symbol, but the one thing that we have yet to discuss is what the atomic mass is, okay? So the atomic mass is essentially just going to be the mass of whatever element we are looking at, all right? But what essentially goes into making up the mass of an atom? Protons and neutrons, right? For an element, can that vary among the isotopes? How much mass each isotope has? Yes, right? So because of that, we have to not just take the isotopes and just average them, but we have to take the various masses of the isotope and essentially weight them according to their natural abundance, right? So if we went back to something like chlorine, chlorine has two isotopes, but one is much more abundant than the other. Would it be fair for us just to take the average of the two and say, that's the mass? No, right? Because of those percent abundances, or those natural abundances, we essentially have to weight each various isotope mass according to that natural abundance. So how would I calculate the average atomic mass for a sample of chlorine if I know that it has two isotopes and I know that they're percent abundances? So we'll show you exactly how to do that now, okay? So chlorine, again, two isotopes. One isotope has a mass of 34.97 AMU, and it has a natural abundance of 75.77%. And the other one has a mass of 36.97 and a natural abundance of 24.23%. So to calculate the average atomic mass for this, what we're going to do is take each isotope mass. So we'll take isotope number 1, which is this guy. So this is 34.97 AMU. And we're going to weight it according to its natural abundance, right? So we have a percentage with respect to natural abundance, but what we have to do is convert this to a fraction, right? So if this is 75%, what is 75%? What is 75% converted to a fraction? Sorry. Well, 3/4, but actual real number, because we want to keep all these sig figs, 0.7577. So just move the decimal 2 places to the left, right? So we're going to take our mass and we're going to multiply it according to the fraction of that isotope. So this is 0.7577. To that, we're going to do the same thing for the other isotope, and we're going to add the two together, okay? So the other isotope has a mass of 34.97, and we're going to essentially multiply that according to its fraction abundance. So this would be 0.2423, 2423, okay? So we multiply these two guys together. For the first one, we will get 26.497. And then for the second one, what we're adding to it, we get a 8.979578. So this is average atomic mass. So then when we add all of these guys together, what do you think it's going to be? It's going to be a number, right? But what should it correlate to? The atomic mass of the element that is given on the periodic table. So when we add these together, we end up getting 35.45. What is the unit here? What are we measuring these masses in? AMUs. And how do I know that there should only be 4 sig figs with respect to this mass that I'm reporting? So our mass had 4 sig figs. Our fraction also had 4 significant figures, right? So this guy was going to be reported to the hundredths place, okay? 4 sig figs. This guy had 4. This guy had 4. This would have gone to the thousandths place. So if I'm adding a number that's reported to the hundredths with a number that's reported to the thousandths, what should I report my final answer to? The hundredths place, right? So rules of sig figs. Not only am I looking for the correct answer for certain things, I'm also looking for the correct reporting of significant figures. Okay, so we've got lots of time, 10 minutes. I'm going to have you go ahead and try determining the average atomic mass of copper. So I give you the 2 atomic masses of the two isotopes of copper as well as their percent abundances. And you should report this with the correct number of significant figures, as well as units. Let me check that before we start. So if you guys want to get a nice green one, or correct answer, make sure to use units as well as sig figs. So really quickly, most of you guys are getting this somewhat correct. I do want to note, anytime I say to use units, I always like to put a space in between the number and the units, right? And it's very particular with respect to Socrative, so if I tell you to use units, make sure to just put a space in between the two. So this one's good. Most everyone's getting the right answer. It ends up being 63.55, and the units are AMU. The only thing I want to note really quickly before we leave is the following. So let's say we're in an exam and I ask for the average atomic mass of an element, and I give you the isotopes and the percent abundances. And I also give you the periodic table, right? What would probably be just the smartest thing that you could do? Look on the periodic table, right? It's going to give you the average atomic mass. You just write that down, or you circle it, etc. So I'm probably not going to ask that, right? I will probably instead ask, if you're given this, and you're given, let's say, percent abundance, mass, and percent abundance, can you solve for the mass of one isotope? Or can you solve for the percent abundance of an isotope, etc.? Okay? So in a real problem, it wouldn't be this cut and dry. There will probably be something thrown in with respect to it like that. Okay? So go forward, have a nice day. Do your homework, it's important.
Just be that one thing.
Thank you too. So for today, what we're going to do, I'm going to talk for like 30 minutes going over the like final rules of chemical nomenclature that you guys should know. And then I'm going to hand out the activities and let you guys do that for the remainder of the time, okay? So hopefully you did the reading or the video assignment before you came to class. So you watched the video I posted, you took the questions or you took the quiz, you did well on that. Hopefully also you did the homework that was due over the weekend. So that was Chapter 1 homework. I will post Chapter 2 homework within the next day, so I would look out for that. And I'll post an announcement on the Blackboard site when I actually do post Chapter 2 homework, so you guys can get started on that. And just as a reminder, we will have an exam coming up in 2 weeks. So our first exam is going to be on the 20th, which is a Thursday of September, and that's going to cover the first 3 chapters. So we're about to finish Chapter 2. We're going to start on chapter 3. It's going to take us a little bit because it goes over quite a bit of information, but then we will take exam number 1 after that, okay? I should also note that with respect to exams, I will give you, I don't do study guides, but I do practice exams, okay? So for exam number 1, I will put up an exam from previous years that I've given, similar time frame, similar material, and I will give you the key to that as well, okay? So just to give you an idea of things that you need to be able to answer questions for, etc., okay? Okay, so in the video, I was talking about naming things, right? I was talking about naming ionic compounds. And there were 2 different ways that you essentially needed to utilize to name ionic compounds depending on the type of metal that you were looking at, okay? So there were type 1 metals and there were type 2 metals. And how do they differ from one another? Type 1 metal, was its charge predictable? Yes, right? So because of that, we didn't have to specify the charge on a type 1 metal ionic compound, right? Type 2 metals, though, those charges were not predictable. So how did we specify the charge of the metal in type 2 metals? We named them Roman numerals in parentheses, okay? So that's what the video assignment essentially went over. So we're going to pick off where I left off with respect to that, okay? All right, so the types of compounds that we were naming with respect to the type 1 and type 2 were what were called binary compounds, okay? So binary compounds is what I went over in the first few different types of rules, okay? And what those refer to, what binary refers to, is that for these guys, we were dealing with a metal plus one other type of element, okay? So it could be multiples of that, but it was only one other element as the non-metal. Okay, so now I'm going to introduce you to how to name ionic compounds that contain a polyatomic ion as opposed to just one other type of element, okay? So, what are polyatomic ions? I did go over this in the video. These guys are covalently bound molecules, right? Things like NO3, NO2, etc. But what has happened to them as a cluster of covalently bound things? They have either lost or gained an electron, right? So we have something that has a covalent bond. Man, my day is not good. Covalent bond, but as a whole, as a unit, they have either lost or gained an electron, so they've formed an ion, okay? So together, they have formed an ion, okay? So when we name these types of compounds, these types of ionic compounds, we are again going to write the name of the metal, depending on whatever the name of the metal is, and then we are just going to name the polyatomic ion. Okay, so with respect to the binary, we always said the base, and then we ended it with IDE. But now, for polyatomic ion compounds, we're just going to write the name of the metal plus the name of the polyatomic ion. Okay, so for example, this compound, to name this, to give it its correct name, I would write the name of the metal. So what is the metal here? This is sodium. I do not have to specify the charge because it is a type 1 metal, right? And then I'm just going to write the name of the polyatomic ion that it's bound to, which is this guy. This is NO3 and it has a 1- charge. This is called nitrate. So nitrate. Okay, so that's how I would name a compound, a metal ionic compound that contains a polyatomic ion. Same thing for this guy down here. I've got copper. And then this thing is another polyatomic ion. This is SO4 2-. That's the charge on it. This is sulfate. So for this one, what type of metal is copper? Is it type 1 or type 2? Type 2. So I would have to specify the charge on copper. If SO4 has a 2- charge, then what is the charge on that copper metal? It's a +2, right? So this would be copper with a Roman numeral 2 in parentheses, copper 2, and then just the name of the polyatomic ion, sulfate. Copper 2 sulfate. Okay, so that's nice, that's easy. The only problem is, how am I getting the names of these polyatomic ions? How do I know that this is nitrate, that this is sulfate, etc.? So there are a couple of different tricks that you guys can utilize to know these, but long term, what it's going to come down to is that you just memorize them, right? I know what nitrate is because I've seen nitrate thousands of times before. Similar type thing, you guys will just have to know the names of these polyatomic ions, okay? So I give you a list here, and I'm going to go through which ones are kind of important that you should focus on, but it's important to note that you not only need to know the name of them, you need to know their chemical formula as well as their overall charge, okay? So a couple of the polyatomic ions that I think are important are acetate and carbonate, as well as this nitrate-nitrite series, as well as these guys over here, not the permanganate. So the hypo all the way to per with respect to the chlorates, and then also sulfite and sulfate, okay? Also one more, sorry, phosphate. These are things that are kind of important later on, so it's important they actually do know the charge of some of these, as well as their chemical formula and name, okay? So if I were focusing on stuff, I would be focusing on these. But what's great about this is, does this require like any conceptual understanding of this at all? All it requires is a flashcard and memorization, okay? Okay, so I will show you one trick with respect to helping out on some of these. So notice that between nitrite and nitrate, so this guy NO2 minus is nitrite, NO3 minus is nitrate. What is the difference between these two? Nitrate has one more oxygen than nitrite, okay? If we go over here to all of these guys with these chlorines and oxygen, what is the difference between each of these individual polyatomic ions? Same thing. Everyone just has one more oxygen than the one above it, okay? So these guys are what are called oxyanions, okay? And so with respect to oxyanions, there are a couple of various tricks that you can utilize so that as long as you know one of the series, you can figure out the other one, okay? So oxyanions, again, are these polyatomic ions that have an element and it's bound to a certain number of oxygens. That's all they differ with respect to one another. They all have the same charge and they're all bound to that same original element, okay? So there are two different types of oxyanions. The first one is the type that has only two polyatomic ions in this series. Okay, so for example, this would be something like nitrate and nitrite. For this group, there's only two of them there, right? Same thing for sulfate and sulfite. There are only two oxyanions that have nitrogen and oxygen in some combination, okay? So for these, what's helpful to note is the polyatomic ion that ends in 8 always has the most oxygen, okay? For the group of oxyanions that only have 2 in the series, okay? So nitrate is NO3 minus. If you know what nitrate is, you can always figure out what nitrite is in the fact that it always has 1 less oxygen than the 8, okay? So if I have memorized what nitrite is, NO3 1 minus, I can figure out what nitrate is. Oh, pardon me. Oh gosh, okay. If I have memorized what nitrite is, If I have memorized what nitrate is, then I can always figure out what nitrite is by knowing that it has 1 less oxygen than 8, okay? So nitrite is NO2 1 minus, nitrate is NO3 1 minus, okay? Again, they all have the same charge with respect to the overall charge of the ion. Same thing for sulfate and sulfite. If I memorize sulfate, I know that sulfite just has 1 less oxygen than that, okay? Okay, so that's groups that only have 2 of the oxyanions in this series. There are clusters that have more than 2 of these polyatomic ions in this series, okay? Their names, though, again, can be derived from the name for whatever the 8 is, okay? So if you remember, or if you memorize what chlorate is with respect to these polyatomic ions, then again, what would chlorite be? So if I memorize that chlorate is ClO3 minus, how could I figure out what chlorite is? 1 less oxygen than 8, right? So chlorite is ClO2 minus, okay, or ClO2 minus up top, right? Then what we use are these little prefixes, okay? So per means 1 more, okay? So perchlorate is 1 more oxygen than 8, okay? So again, if I know chlorate and I have perchlorate, I know it has to have 1 more oxygen than whatever the 8 was. And then hypo as a prefix means one less than. Okay, so hypochlorite is one less oxygen than whatever the ite was. Okay, so if you memorize chlorate, you know that chlorite has one less oxygen than that. Hypochlorite has one less oxygen than chlorite, and then perchlorate has one more oxygen than chlorate. So my recommendation would always be to know what this guy is. You can figure out the rest from that. And again, these guys don't differ with respect to charge. They all have the same 1- charge, so they're all going to have the same charge in this series. Okay, so that's nice. That's helpful. Let's go ahead and utilize that and do a question, okay? So at this point in time, what you should note is how to name type 1 and type 2 binary ionic compounds, and also how to name ionic compounds that contain polyatomic ions, okay? I'm going to skip ahead to this one, and I'm going to put this on Socrative. So I provide you the formula, and I want you to type in the name, okay? If you want to get like a good green box and everything, make sure that everything is lowercase, and make sure there is a space where there needs to be a space in between words. So write everything in lowercase. Okay, so go ahead and get your answers in. We'll go over these in a minute. Okay, so most of you guys did pretty good on this. Going through these, again, you have to keep in mind type 1 versus type 2 metals, and then you have to know the overall charge with respect to polyatomic ions, as well as just binary single elements by themselves. Okay, so on this first formula that we have, MgCl2, is this a type 1 or type 2 metal? Type 1, right? Super predictable. Magnesium, it's group 2, so magnesium, and then I don't have to specify the charge because we already know it. And then what should I begin with respect to the non-metal? Base name of the non-metal, this is chlorine, so we have chlor, and then what do I end it in? IDE, okay, magnesium chloride. Same thing for the second one. Is this a group or type 1 or type 2 metal? Type 1, so sodium, predictable, has a +1 charge. What is this polyatomic ion? Carbonate, right? And so with respect to polyatomic ions, you just write the name of the polyatomic ion. You don't have to worry about the IDE. Same thing for this one. What is this polyatomic ion? OH. This is hydroxide. That should have been another one that I mentioned. You should know what hydroxide is, but you will later on because it's important with respect to acid-base chemistry. So this is calcium hydroxide. What about this guy? CuCl2. So this is a type 2 metal, right? We can't predict the charge of the copper just by looking at it. So to specify that, we have to say what charge it is. This is, what is the charge of copper here? This is 2+, so this is copper 2. And then base name of nonmetal, chloride. What about this guy? This is kind of a weird one. This is the only positively charged polyatomic ion. Okay, so there's only one positively charged that you guys need to know. This is ammonium. And then the second one, NO3 minus, is nitrate. And then this last one, FeNO3. What is the charge of Fe? Who is Fe? Iron. So iron, and then what is the charge here? 3. And then nitrate again. So NO3 has a 1- charge. There are 3 of them, so this guy has to be a +3 because of that. Okay, so that's, again, kind of, yes, go ahead.
So in the last one, it was, I got it wrong because it said nitrate, and the answer it gave us was nitrite.
Oh, my bad. It doesn't count against you in socrative. I'm just looking for participation, but this is nitrate, so I must have typed it in incorrectly in socrative. Yes?
In socrative, it was NO2.
Oh, yeah. So, sorry, sometimes these get mixed up when I type stuff in. We all make mistakes, and it's not going against you. So yes, in socrative it was listed as nitrate, or nitrite, but here I have it as nitrate, so we'll just go with it. Okay, so moving on. More things we have to talk about, and then we'll do the activity. So that was all with respect to ionic compounds, right? Ionic compounds are between metals and nonmetals, so we have charges that helps lead us in the naming. What about molecular compounds, though? What are they made up of? Molecular compounds, they consist of covalent bonds, right? So what type of elements make up covalent bonding? Metals? No, right? So what are molecular compounds made up of? Nonmetals. So it's a nonmetal plus a nonmetal. How do you know you have a molecular compound? Because you have a nonmetal bound to another nonmetal, okay? So because of that, we don't get charges, right? With respect to ionic compounds, the charges help us name or know what type of compound we're dealing with coming from the name, okay? We don't get charges in molecular compounds. And also, another issue that we run into is that any two elements can form a variety of different type of compounds, right? So for example, nitrogen and oxygen, they can combine to form NO, they can combine to form NO2. There are a variety of different things, right? So we couldn't just call one of them nitrogen oxide, okay? So to help us in specifying this, what we will utilize when we are naming molecular compounds is prefixes, okay? And the prefixes are going to tell us how much of whatever element we're dealing with we have, okay? Okay, so what are the prefixes that we use for molecular compounds? So you guys should know these. And for the most part, they're kind of already nice and laid out for you, right? So if you have one thing, the prefix you use is mono. Two things, the prefix you use is di, tri, tetra, so on, all the way to deca, okay? So that's if you have 10 various things. So how we're going to utilize these prefixes in naming these molecular compounds is we are going to list the prefix for the name of the first element, okay? So prefix, name of first element, space, prefix, base name of second element, followed by IDE, okay? So for example, if we are naming this guy, what is the first element that is given in the formula? Nitrogen. How many of them are there? 2. So if I'm going to denote that, I have to say di, because that's the 2 prefix, dinitrogen. And then what is my second element? Oxygen. How many of them are there? 4. 4 corresponds to tetra. Tetra, and then we just say the base name of the second element ending in IDE. So the base name of oxygen is ox, and then I'm just going to end it in IDE. So one thing to note, with tetra, we end in A. With oxygen, we start in O, right? That's 2 vowels. We usually don't like to do that. So with respect to something like this, we tend to get rid of the A. So this would end up being tech, ox, and then IDE. So prefix, element, first element, and then prefix, base name of second element, ending in IDE. So what would this guy be? NO. How would I name that? So if we have only one, what do we say? It's mono, okay? But for these guys, if there's only one for the first element, we can always just omit the first mono, okay? So we don't have to say mononitrogen. We can just say nitrogen, and the mono is implied, but then I do have to specify how many I have of the second one, right? So what would I go with here? So this would be mon, and then again, I don't want to follow with 2 vowels, so I'll drop one of the O's, mon, ox, and then ending in IDE. Okay, so this one, because again, we don't have charges, we have to specify how much of each element we have. We do this with these prefixes, and again, you should be familiar with all of these prefixes. Okay, all right, so one more thing. This was molecular compounds. There's one more little nomenclature that we have to talk about before we can start the activity, and that has to do with acids. So have we talked about acids yet? No. Okay, so acids are special, and that's why they have their own special little nomenclature, okay? So acids are things that are molecular compounds, so things like HCl, right? How do you know this is a molecular compound as opposed to an ionic compound? It's composed of 2 or more nonmetals, right? So H and Cl, those are both nonmetals. But from these types of molecular compounds, these acids, when you put them in water, instead of being cool and molecular, they actually act as if they were ionic. So they break apart into these little ions, okay? So again, what are acids? They're molecular compounds that when you put them in water, behave as if they were ionic compounds, okay? How do we denote that this is in water? So we use this little physical state AQ, which stands for aqueous, okay? This means that this is being dissolved in water, okay? How do you know you have an acid? It's usually denoted by there being a hydrogen up front, okay? So if you have a chemical formula, there's a hydrogen up front, and you are followed by an AQ, you know you have an acid, and you need to utilize the acid nomenclature rules, okay? So what are those acid nomenclature rules? So we have two of them, depending on the type of acid we are dealing with. So the first type of acid we call binary acids. This again is going to be an H plus some other type of element, okay? And then the second types of acids are called oxyacids. Again, they're going to be a hydrogen, but what do you think they're going to be bound to? We call them oxyacids. Probably a polyatomic ion, an oxyanion, okay? So binary acids versus oxyacids, we have two different rules depending on what we're dealing with, okay? So we're going to start with the binary acids first. So these binary acids are going to be things like HBr, HCl, etc. Okay, they're going to be hydrogen bound to only one other type of nonmetal, okay? And so how we name these is we're going to identify, first off, that it's an acid, but we're also going to identify that it's a binary acid. So we're going to use this little prefix hydro first, then we're going to write the base name of the nonmetal that the H is bound to, and we're going to end it in IC, and we're going to put a space, and we're going to write acid, okay? So for example, this guy is a binary acid, HF. The first thing we're going to do is write hydro, because it's binary acid, and then what is the base name of this nonmetal that it's bound to? Fluor, right? So hydro, then I'll write fluor, and then what am I going to end it with? Ic. So hydrofluoric space acid, okay? Same thing from this guy, another binary acid, so I write hydro, I use that prefix, hydro. What is the base name of this one? It's an I. Iode, hydro, iode, and I'm going to end it in IC, hydroiodic acid, okay? Okay, so anytime it's a hydrogen with just one other type of nonmetal, you're going to use these rules. It has the hydro prefix, you end the base name with the ic, and you write acid, okay? Now, the last rule is for naming oxyacids, okay? Again, these are going to be acids that contain a polyatomic ion. So this is going to be things like HNO3 and H2SO4, etc. Okay, these are acids of polyatomic ions. Okay, so how are we going to name these? Number one, we never use the hydro. The hydro is only for binary. Okay, so never put hydro in front of any type of nomenclature with respect to these oxyacids. Number two, the name of it is essentially going to depend on whatever name we have for the oxyanion. Okay, so for example, if we had this guy, this is HNO3, what is the name of this polyatomic ion? So this is nitrate, so this ends in 8, okay? So if you have an acid with a polyatomic ion that ends in 8, we're going to end it in ic, okay? So because of this, this becomes nitric and then acid, no hydro, okay? On the other hand, if we had something like this, HNO2, this is nitrite, right? So this is the acid of nitrite. If the polyatomic ion ends in ite, we're going to end it in OUS instead, okay? So if the polyatomic ion ends in 8, we end it in ic. The polyatomic ion ends in ite, we end it in OUS. So for this guy, it would be nitrous acid, okay? So no prefix, just the base name of the polyatomic ion, end it in ic if it ended in 8, end it in OUS if it ended in ite. And then one last thing, I'm going to go and let you guys get started. How do we go in reverse with respect to these acids, right? What if I gave you the name sulfuric acid? How would you know what the actual chemical formula is for that? So number one, does it have hydro? No. So what does that tell you already? It's a polyatomic ion acid, okay? Number 2, it ends in ic. So what does my polyatomic ion have to end in? 8, right? So I know this is the base of sulfuric or whatever. So this has to be SO4 2- because this is sulfate. And now if I wanted the chemical formula for this acid, what else do I have to keep in mind? The charge on the proton. H's always have a plus charge. When I combine these two to get the chemical formula, I have to combine them so I have a charge neutral species, right? So how many H's do I need to balance the 2- of the sulfate? 2. So if I was going from the name of the acid to the chemical formula, I have to keep those things in mind, and the chemical formula for this would be H2SO4, okay? What about hydrochloric? What is that telling me? Hydro? It's a binary one. What is the anion that I'm dealing with? Chlorine. So I know it's a Cl- because, again, that's a predictable charge. How would I balance this with my H+? Just 1-to-1, right? So again, given the name, how do you get the formula? You break it down for each individual rule, and then you balance it with respect to charge, okay? All right, so let's go ahead and get started. This is going over these various types of nomenclatures. So it mainly just deals with molecular and ionic. It doesn't go into the acids. I would go ahead and come and pick up one of these. I have 90 for all of you. It would be helpful if you stuck in the same groups, but you don't have to, okay? I will pass back activity number 1, though. So if you're in the same groups, it makes it a lot easier on me. And then number 2, the manager today is the person who closest to Tucson. So hometown or home closest to Tucson, that is who the manager is today.